All right, it's 1:20, so I'll get started with a few announcements. Just run through the calendar for the rest of the course. So let's see, today, as I was just saying, we're going to finish up lesson 8 and hopefully get partway into lesson 9. Homework 8 is due tomorrow at noon. It was today, but we postponed it till tomorrow because I haven't gotten through all the material yet. Then we have a class on Friday where I'll get through most of the lesson 9 material. Whatever I don't get through, I'll just assign as an extra video that you can watch over the weekend. My old video on that extra material is not very good, so I may reshoot it, in which case it may not be available to later in the weekend. But we'll try to wrap up everything tomorrow with lesson 9, except for the search for extraterrestrial intelligence. We're going to spend a whole class on that. It's a fun topic. So that will be Monday, and we'll make use of our e-polling interface. There's a different functionality you haven't seen yet. And so throughout the entire class, we'll be using that pretty aggressively, talking about the probability of life elsewhere in the universe. Then homework 9 is due Tuesday of next week, but I've postponed it from noon until the end of the day on Tuesday, 11:59 p.m., just to give you a little bit extra time. And also to make time for office hours. I'll have office hours next Tuesday for anyone who has questions about the homework. And I'll have office hours again on Friday next week for those of you getting ready for the exam, which will be on Monday, November 23rd, as we all decided. It'll be released at noon and be due at noon on the next day. I know that's a lot but to take in, but that's the calendar for the rest of the course. The final exam, I'll talk more about it next time, I guess, but it is cumulative with an emphasis on the new material, and it'll be longer, probably about 70 questions. And it's normally a 3-hour exam. Again, you'll have a 24-hour period to do it, and half the questions will be on exams 1 and 2, so lessons 1 through 6, and half of it will be on the new material, lessons 7, 8, and 9. Which we're covering pretty quickly, but they're short lessons. Any questions about anything before we get into this warm-up question?
Yeah, I have one question. Is it going to be like the midterms where we're going to know our grades immediately after the testing period's over?
Yeah, so you'll know your score immediately, and I'll try to update the score to grade conversion spreadsheet, though at that point, I'm essentially putting the grades in as well. So whether you come back to the spreadsheet in WebAssign or whether you check your grades online, it'll happen pretty quickly at that point.
Okay, and how does the like dropping the midterm or is like half of the final?
Yeah, think of the final as 2 midterms. So in total, you have 4 exams. It's really 3 exams, but the final counts double. So it's like 4 exams, and the spreadsheet automatically will drop the weakest of them, the one that hurts you the most. You don't have to email me and tell me which one to drop. The spreadsheet will figure it out to your benefit. Also, there's the extra credit. For those of you who need to drop a second homework, you can find an extra credit essay in the Lab 5 ebook at the end. Just follow the directions, turn it in with the final on that day, not earlier because I'll lose it in my inbox, and not later because it'd be too late. Turn it in on that day, and you can drop a second homework. But that's only if you need to drop a second homework. Otherwise, it does not make sense to do it. Other questions? Okay, let's take a look at this warm up, and then we'll just keep.
Wait.
Oh, go.
I'm sorry. Can you repeat the extra credit? So is it just for people in the lab, or do you say it could be found in like a lab ebook?
I might have misspoke. It's in the WebAssign ebook, which is not really a book. It's just a collection of notes. Yeah, you've seen it.
And it'll say extra credit.
Yeah, it's extra credit. It's a 2-page essay. It's at the bottom of lesson 5. I might have said lab 5. I meant lesson 5.
Gotcha. Thank you.
Sure. Anything else? Okay, let's take a look at this warm-up question. There's a lot to it, so I'm just going to throw you in the break rooms. I'm actually going to clear the board, so if you've already submitted, you'll resubmit after talking in the break rooms. You may change your mind or change someone else's mind. But for the planets that we've covered so far, Mercury through Saturn, we spent some time talking about the different causes of tilts. Some of the planets are tilted, some are not, all for different reasons. I want you to put them into these categories. And so you'll have, it's a 6-digit number that you'll submit. And so these are the categories. Category 1 is the planet's tilt wanders due to random gravitational tugs by other objects in the solar system. Option 2 is it does not wander because the planet's just too massive for this. The massive planets can't be affected by random gravitational tugs. Instead, if there's a tilt, it has to be due to impacts, big ones. Option 3 is the planet's tipped due to non-random resonant tugs. We talked about this. It's like pushing a swing. As long as those tugs are not random, but at carefully timed intervals, you can actually move large bodies, tip them over. Option 4 is the tilt is locked in due to tidal forces with the sun. And option 5, the tilt's likely due to a major impact, and it's now locked in by tidal forces from a large moon that resulted. Okay.
Professor?
Yes.
How are we supposed to format our answer?
So for Mercury, you pick one of these 5. For Venus, you pick one of these 5. For Earth, you pick one of these 5, and so forth. So you'll end up with 6 numbers, and put them in a row and submit the 6-digit number.
Okay, thank you.
And there's so many possible variants, it's probably going to come back as a terrible mess, but we'll just see what happens. So let me go and let's see, breakout rooms. And let's see, currently there's about 80 of you. If I want 5, so let's do 15 rooms. Assigned automatically, creating the rooms. They're all open. I'll give you like a minute and a half, maybe even 2 minutes. Go for it. Oh, and copy, screen capture before you go. Okay, everyone's back. Get rid of that. Okay, so type in your 6-digit number. Okay, let's take a look what we got. And this always comes back as a terrible mess. But let's see, one of these numbers is favored. Let me go to the fewer bins, making it easier to read. 415123. Hey, perfect. That's it. That's great. So just running through them really quickly. Most of you got it right. So Mercury falls under category 4. It's locked in due to tidal forces with the sun. The sun has tidally stretched it out, and that stretch wants to point directly at the sun, so no tilt with Mercury. Venus and Mars fall under category 1. They're small planets, nothing to stabilize them, so they wander around kind of randomly, can even flip over given enough time. Enough of these random gravitational interactions with the other planets. Earth falls under category 5. We likely had a major impact, and that formed the moon, and the moon is now locking our tilt in through its tidal forces. Then we have Jupiter and Uranus and Neptune, although they weren't part of the question, and you'll see they fall under the same category. These are gas giants. They're too big to wander randomly through these random gravitational tugs. You can't tip them over that way. So it's most likely a major impact responsible for the tilt. Jupiter, it's only about 3 degrees. So there's nothing Jupiter size that hit Jupiter, not in our solar system. In other solar systems, we do see evidence of stuff like that. But Uranus and Neptune are much less massive, as we'll learn. They've been tipped over tremendously. So they've probably been hit by some pretty big stuff, big comparable to their sizes. And then Saturn was the exception among the gas giants. It is in a resonance with Neptune, where Neptune is doing these little tugs, but they're always at just the right time. Again, like pushing a swing that has tipped Saturn over the past 4.5 billion years. Okay, very good. A lot of information in there, and you all organized it correctly, so that's nice. All right. So we left off, I'm just going to jump right in here. We'd gotten through most of Saturn. We did Saturn, the planet. We got through most of the rings. We just have the outer rings left to explore, and the moons, and then Uranus and Neptune, and then on to lesson 9. So these outer rings, the first one we encounter is F. You may remember we left off talking about the Cassini division, which is the 2-1 destructive resonance with Mimas, and all the detail and structure in here is due to other resonances with Mimas and the other moons. We talked about these 2 gaps at the end, the Encke gap and Keeler gap, due to single overdense moons orbiting in the outskirts out there. But then we have ring F, and beyond that, G and E, and we'll look at them. Well, let's start with F. If we take the F ring and stretch it out, this is the whole ring stretched out into a single image, you can see it has a lot of interesting structure. It's just not stuff floating there. There's something definitely disturbing it, messing with it, creating this ripply pattern. And it's a thin ring, but it has this, this weird ripply pattern, which is caused by what we call shepherd moons. And this is going to be important. We're going to see rings around other planets, thin little wispy, piddly rings, leftover rings. These are held in place by pairs of moons. Ring systems like Saturn's, it's not permanent. Those rings will fall apart with time over the time scale of about 100 million years, which means that the moon that broke apart and caused them probably came within the past 100 million years. But what will be left over is anything that gets trapped between pairs of moons. If you have two moons at about the same distance, they together act as a gravitational lens of sorts, and anything caught between them stays between them, can't escape. One of them pushes it away, the other pushes it back. And so even after Saturn's rings are gone, the F ring will still be there. That material is never getting out. And there are probably going to be other thin rings that they're probably tiny little moons distributed in the outer parts of the rings that we don't even know about. And whenever you have a pair, again, we call them shepherd moons, the stuff between them stays there essentially forever. Those two moons are called Prometheus and Pandora, and they shepherd the F ring. Now, to see the other rings, it helps to have this, to back illuminate them. This is one of my favorite pictures of Saturn, taken by Cassini, and the sun is behind Saturn. So the sun is back illuminating everything. You see the details of the rings, the A ring, the B ring. My favorite part is this little blue dot right there. That's us, that's Earth. There's a 50% chance you're in that picture, depending on which side was facing the Cassini spacecraft when it was taken. Then you see some rings out here. Let's put labels on them. Here we have the F ring, which we just discussed. You have a G ring. We're not really sure what's causing that, whether it's shepherd moons or whether it's something like we see in the E ring. In the E ring, we see only one moon, not two moons holding it in place. There's just one moon in there, right in the middle of the E ring. It's Enceladus. There it is. And here's a close-up picture of it superimposed next to Great Britain. It's one of the medium-sized moons of Saturn. We'll talk about the moons in just a little bit. There's one large moon, but there's a handful of medium-sized moons. This is one of them. By medium-sized, this gives you an idea of scale. And looking at it, you can see it's covered in ice, and the ice is very white, which means it's new. It's a surface that is new or constantly being refreshed, because we learned with the moons of Jupiter, the longer the ice is exposed to space, the darker it gets. So something is constantly recoating this moon. Here's another picture of it, and you can see water spewing from the surface. It has geysers. So this moon, like almost all the moons out here, it's tidally locked to its planet, Saturn. But in this case, there's another moon messing with it. The moon Tethys is the next moon out, and it's a medium-sized moon, but much bigger. And so it's messing with the tidal locking, causing tidal heating. So just like with the Galilean satellites of Jupiter, we have tidal heating going on. This is a small moon, or a medium-sized moon, but small enough that it would have lost its heat of formation a long time ago and would just be a solid block of ice by now. But because of the tidal heating, it's melting the water. So it's kind of like Europa. You have ice, but underneath there's an ocean, and the ocean is just bursting out, spewing this water all over the surface, recoating it, keeping the ice very white. But also a lot of that is leaving at greater than the escape speed, which forms the E-ring. The E-ring's constantly falling apart, but is constantly being replenished by these geysers from Enceladus. And it's kind of similar, it's analogous to the Io plasmatorus. If you remember, Io is being tidally heated to the point that it's melted its mantle, making volcanoes spewing rocky particles. But same idea, it's spewing particles that are being dragged around into the Io plasmatorus, dragged by Jupiter's magnetic field in this case. Here you're spewing water, also leaving a trail. So some analogies and similarities there. Okay, those are the rings. Now let's tackle the moons. And we have medium-sized moons. With Jupiter, we didn't. We had 4 large moons and no medium-sized moons, and then a ton of small captured asteroids. With Saturn, we do have medium-sized moons. There are 6 of them. We've already encountered Mimas, responsible for the Cassini division, Enceladus, responsible for the E-ring, Tethys, which is disturbing Enceladus to make the geysers in the E-ring. And then you also have Dione and Rhea and Iapetus. And this is their sizes compared to our moon, just for
Excuse me, Professor.
Go ahead.
What exactly separates, like, as far as classification goes, separates like a medium moon versus like an asteroid, I think you said?
Yeah, it's a little bit arbitrary, and different people will divide it different ways. The 7 big ones are pretty distinct, and there's a bit of a gap before, here are the 7 big ones of the solar system. And then there's a bit of a gap where you had, off the top of my head, I can't think of the actual sizes. I might have it here, one second. Let me look under Neptune, its moons, if I have the size here. Yeah, I don't have it written down, but it's a little bit arbitrary. Once you get below a certain size, they're just a ton of small things, mostly captured asteroids. These are objects for the most part formed naturally.
Okay, thank you.
Yeah, sorry, I don't have the numbers off the top of my head, but that's kind of the distinction between the large and medium and the small. The small things are almost always captured stuff. Okay, so going around Saturn, we have the 6 medium-sized moons here. And, we're not going to go into them in detail other than the interesting ones we've already talked about. But we have one large moon as well, Titan. Yeah, here we see Earth's moon, the 4 Galilean satellites of Jupiter, and now we have Titan around Saturn. And Titan, well, you can see here, it's the same size as Ganymede. It turns out it's the same mass as Ganymede, so the same density as Ganymede. That means the interior of Titan probably looks a lot like the interior of Ganymede, with a rocky, a metal core, a rocky mantle, and then a whole bunch of water, probably in a icy or slushy state. And then you have the surface ice. And this has been confirmed. Cassini has an orbit like this, and it can readjust its orbit and have all sorts of close encounters with the moons. It's had lots of close encounters with Titan, and has taken gravitational measurements and can kind of confirm that interior structure. We have a rocky or rocky metallic core, then above that, different layers of ice and slush before you get to the surface ice. So it's an analog to Ganymede, with the one difference being it's twice as far from the sun. Ganymede and Jupiter, they're about 5 AU from the sun. Saturn and Titan are about 10 AU. It's farther away and it's cooler. So this world is cooler in temperature, which means it can retain its atmosphere. We talked about atmospheric retention. It depends on the temperature and the escape speed. The escape speed for Titan is about the same as the escape speed for Ganymede. But the difference is being twice as far from the sun. It's cooler out there. The gases are moving more slowly, and so it can keep them. Not the hydrogen and helium, but the water, ammonia, and methane. Come back to that in a second. But it makes it hard to see the surface. It's kind of hazy, this orange ball. Though if you look in the infrared, you can penetrate the haze layers and see down to the surface. And Cassini does have an infrared camera, and I think we came across this picture in lesson 5 briefly. And we see light regions and dark regions. Those light regions, that's frozen water ice. It's cold. It's 94 Kelvin, which corresponds to negative 290 degrees Fahrenheit. So definitely cold enough the water will only exist in solid ice state. The dark regions, we think that's methane. At these temperatures, methane can be in a liquid state. In fact, just like water on Earth is in all 3 stages. We have some solid ice water, we have liquid water, and we have water in a gaseous state as water vapor in the atmosphere, like clouds. We think the same is true for methane on Titan. The temperatures are just right. So these are probably methane lakes, or at least were methane lakes at some point. It could be, for most of these, it's leftover residual methane sludge. So kind of a solid state of methane. So
What did you say the light regions were?
Ice, water ice. So let's talk about the atmosphere. This is kind of how it's structured. And this has been confirmed by a probe that we dropped through it, but this was the expectation beforehand as well. Let's talk about composition first. I'll go to the dot cam for this. So again, we're not going to hold on to hydrogen and helium. It's not a gas giant or anything. So the next things we have to think about is the methane, the ammonia, and the water. And with the water, and this is all under heading of Titan. The water, it's so cold there it freezes. So it's water ice. The methane, we said it liquefies. And actually all three states, but kind of liquid is the most interesting, which means, if it's liquid, there should be lakes, which means there should be evaporation and methane rain. Anyway, in a liquid state. And then the ammonia, the same thing happens as happened on Earth. NH3, this ammonia gas is just hanging around, bumping into other NH3, and that produces N2 plus 3H2. And the 3H2 is very lightweight, is lost to space, but the nitrogen gas, molecular nitrogen gas, sticks around. And so that's what the Titan atmosphere is almost exclusively made of. Just like Earth's atmosphere is primarily nitrogen gas. We also have oxygen gas released by plants, but before the plants, that wasn't there. So very similar to Earth in that it's mostly nitrogen. It's mostly N2, but there's a few percent of methane, which is CH4. Again, just if you have liquid methane, some will evaporate, so there's always going to be a little bit in the atmosphere. Just like here on Earth, there's always a little bit of water vapor in the atmosphere. And after that, you have trace amounts of some pretty noxious stuff. Ethane, propane, carbon monoxide. It's probably good there's no oxygen on Titan, because a lot of the stuff is really flammable. You could light a match and the place would just burn. Okay, so that's the atmosphere. Now, another interesting thing about the atmosphere is it has about 10 times as much gas as Earth. I'll put that down. 10 times as much gas as Earth. It's cold there, it can retain a lot of it, even though it has lower surface gravity. And because of that lower surface gravity, it's not squeezed very tight. You can see how high up the atmosphere goes. It's about 7 times thicker than our atmosphere. So 10 times more gas and 7 times thicker. It's a very impressive atmosphere compared to even our own. On Earth, 12.
Sorry, Professor, question.
Yeah.
What exactly is the difference between like having more gas and like being thicker? Like,
Well, those two kind of go together. There's more material. If we were to take all the gas on Earth and measure how much there was, and all the gas in the atmosphere of Titan and measure how much, we'd have 10 times more stuff from Titan. But then it's a matter of how thick is it, how much you compress it, and that depends on the surface gravity.
oh, okay.
Yep.
I think I understand now.
Surface gravity on Titan is 1/7 that of Earth. So it's a lot puffier. Like, think the cloud tops of Saturn versus Jupiter. Jupiter had the higher surface gravity. Those cloud layers are squished thin, but they're thick on Saturn. Here, it's like an Earth atmosphere minus the oxygen, but thick. On Earth, we consider 100 kilometers the boundary of space, and you can see the atmosphere is just beginning there. And down here, you see clouds. Again, those would be methane clouds, not water ice clouds like we have here. Anyway, that's the expectation. And it was confirmed because we dropped a probe through there. On the Cassini spacecraft, we had a probe called Huygens, and we dropped it, and Cassini dropped it into Titan. And a couple of fun things here. First, I have audio. That goes on and on, but you get the idea. There's an atmosphere. They just put a microphone as it went down. So there you're listening to the atmosphere of another world. And it took pictures on the way down. Here's the sequence. And a lot of them, you don't see anything, but some of them have some really interesting structures. And I'll let you look and find them as we go through. Saw some there. As we get closer to the ground, we see more detail. It's almost on the ground. There. And I'll put up that last picture. It landed on the surface, and it was designed to land in such a way that it wouldn't break. And we had about an hour until the batteries ran out. So it took this picture, and those are not rocks. All the rock is deep in the interior. These are ice balls. It's a frozen ice wasteland with ice balls on it. And the coloration is just due to the haze in the atmosphere gives it this very orange color, kind of like on Venus.
Dr. Rahman?
Yes.
So I was wondering, since it has like an actual atmosphere and some form of like liquid on the surface, is it possible that there's life there?
Yes. And it's something that we'll come back to when we talk about SETI on the last day. But the requirement for life, as we talked about before, is carbon and a liquid in which the carbon can move and come together and form complicated structures. For us, that liquid was water, but we have water, ammonia, and methane as the big three things. Ammonia never really enters a liquid state of use for the temperatures in the solar system, but in the cold parts of the solar system, you can have liquid methane. And so there's the possibility of carbon methane life. It's speculative, but possible. Anyway, here's a stitch of all those photos. They were able to arrange them, put them down, and it looks like they're rivers. Again, this would not be water. This would be liquid methane flowing into a methane lake. Now, they studied these images very carefully, and it's not flat. The dark region's not flat, so it's probably not full of any liquid right now. It's probably sludgy residue. This was probably a methane lake at one point. And they've looked for the lakes and they found them. These are radar maps. Every time Cassini would fly over, it has radar built into it as well. And it's found these regions that are indeed perfectly flat, which is really suggestive of liquid being there. So there are what we think are methane lakes near the poles, in the northern region in particular. These white spots are just data dropouts. It's not a complete, this was a composite, lots of data put together to produce this. Here are a couple fun pictures. Here's sunlight bouncing off one of these northern methane lakes through the haze. And here's another one. This is in the infrared where, again, you see sunlight bouncing off different lakes and coming back up into the camera. A really interesting world. Anyway, that is Saturn. Questions about Saturn before we tackle Uranus and Neptune together? Okay, so Uranus and Neptune, they're very similar, so we'll just handle them together. And we know the least about these, so it goes pretty quick. What we do know, we know primarily from Voyager 2. It's the only spacecraft to have visited these two worlds on the Grand Tour. And here's Uranus and Neptune compared to Jupiter, Saturn, and Earth. So clearly bigger than Earth, smaller than Jupiter and Saturn. Let's look at the bulk properties. So about 4 times the size of Earth, where Saturn and Jupiter are about 10 times the size. Mass is maybe about 15 times the mass of Earth, where Saturn and Jupiter are much more massive. But again, we can calculate our 3 favorite things. The average density is still consistent with compressed gas and ices in there. And surface gravity, so at the cloud tops, it's similar to Earth, just like with Saturn. And the escape speed is lower, but again, you're farther from the sun, it's cooler, it takes less escape speed to hold the gases in, and this is sufficient to hold in hydrogen and helium, enabling you to be a gas giant. You're not a gas giant if you can't hold the hydrogen and helium. So there's so much of it, that's what makes you a gas giant. Those are the basic properties. Now, as we kind of hinted at in the warm-up question, these gas giants have been banged around. They don't wander on their own, they're too big for that. But if they get hit, they can be knocked over, and they're a lot smaller than Jupiter and Saturn. And so it appears they've been hit. Neptune's tipped considerably, and Uranus is tipped all the way over, or at least on its side and a little bit, which means technically it rotates backwards because it's been flipped just a little bit past 90 degrees. And it makes for some really interesting day-night seasonal patterns on Uranus. So imagine living on the equator or floating in the cloud tops on the equator of Uranus, it goes around, it rotates on its axis once every 17 or 18 hours. So you'd have day, night, you know, over a 17 or 18 hour span over and over and over again if you lived on the equator in this position. For about 2 decades, it'd be like that. But then you'd move over here. And if you're on the equator, then it's constantly twilight. The sun is just on the horizon, going around in circles every 17, 18 hours. And then you come back here, and that would go on for a couple decades, and you come back here, and then it's, you know, daily cycle, and then come back here, and it's on the horizon again, going the other direction. Now, if you lived on a pole, let's start here. If you lived on the pole here, you would see the sun on the horizon whipping around every day. And then you'd move over here and you'd have decades of darkness. And then back over here, you see the sun whipping around every day in the other direction. And over here, decades of illumination. It's a very strange day, night, and seasonal patterns on a world that's tipped on its side. The interiors, here's Jupiter and Saturn again. And in the case of Jupiter and Saturn, we did have the metallic hydrogen. Primarily with Jupiter, we had a ton of it. With Saturn, it didn't have as much mass, not as much gravity, so we didn't have nearly as much, maybe 1/14 as much, or something like that. The magnetic field is 1/14 as strong. So as we go down to Uranus and Neptune, there's not going to be enough material or squeezing to have any metallic hydrogen. We barely have any with Saturn compared to Jupiter. With Uranus and Neptune, we don't have any metallic hydrogen, but we still have a conductive fluid. So this is our third type of magnetic field generator. We talked about liquid iron with the Earth, metallic hydrogen with Jupiter and Saturn. And with Uranus and Neptune, you're farther from the sun, it's cooler, and the water and the ammonia has kind of sunk, it's differentiated. Just like on Saturn, the helium was liquefying and raining down. And that process is done out here in the outer solar system, but also water and ammonia has kind of moved on down and formed a slushy layer. It does move. It's not solid, but it's a slushy layer down beneath the hydrogen and helium. And that water ammonia layer is conductive. And so we have rapid rotation, we have a conductive fluid, so you're going to have a magnetic field, but it's kind of a strange magnetic field. It's being produced by a different type of material, water ammonia slush, and these planets are tipped over, so they're rotating kind of funny. So you end up with these magnetic fields that are misaligned with the rotation axis and offset. Basically, the core is large compared to the size of the planet, and so the magnetic field you don't form this kind of global magnetic field centered on the center. It has to live on one side or the other in this slushy layer. So it's offset, and its alignment is large. You know, these you can see are very aligned with the rotation axis. This comes out misaligned. And the reasons why they continue to study this, they're trying to figure it out. It's really peculiar, but it ultimately has to do with a different type of material generating it and the weird rotation being, you know, on its side. Okay, so we have these offset, misaligned magnetic fields, but their strength is similar to Earth's. These are strong magnetic fields. Let's talk about coloration. So again, review. With Jupiter, we had thin cloud layers. Sometimes you can see through one to the next in breaks in the cloud layers. And so we see all these different colors from different depths, different temperatures, different sulfur reactions, making this intricate, varied pattern of browns on Jupiter. But Saturn, we don't have as much surface gravity. That upper layer is really thick, so that's all we see. It's ammonia ice and it's butterscotch or yellow in color. So here's Saturn with its yellow surface. But as we just learned with Uranus and especially with Neptune, the ammonia has sunk down from the surface layers down underneath, becoming part of this water ammonia slush. So if you take away the yellow ammonia, you're left with kind of a blue world. And this is just caused by light bouncing around. It's the same reason Earth's sky is blue and Earth looks blue from space. It's just light bouncing around. The short wavelengths bounce around more, so it colors the planet blue. Uranus is in between. Some of the ammonia has sunk down, but not all. So it's a mix, yellow plus blue makes green. So again, these wildly different details of the planets. One is yellow, one is green, one is blue. You've always known that since you were drawing pictures of these in grade school as a kid. But you can see it has common explanations. Okay, internal heat. Uranus doesn't have an extra source of heat. It lost its heat of formation a long time ago. The helium rain has ended. It's ongoing in Saturn, causing its source of heat, but it's ended here. It's in equilibrium with the sun. The temperature is exactly what you get from our temperature equation for a rapidly rotating atmospheric body. And this means it's going to have the least violent weather of all the gas giants. Weather's mostly driven by that extra heat coming from the interior. This is just the heat from the sun. So the weather is pretty mild. Occasionally there are storms. We can track them to measure the wind speeds, and they're the lowest of the gas giants. But if we look at Neptune, it has a lot more hurricanes. They move quickly. You have some pretty high wind speeds on Neptune. And in the case of Neptune, it's 2.7 times as much. So Jupiter, Saturn, Uranus, and Neptune. Jupiter was times 2, Saturn times 3, Uranus times 1, Neptune is times 2.7, almost as strong as Saturn. It has an internal source of heat with more heat coming out than going in. And we'll learn this is because of where it formed. In the next lesson, we'll learn that things that form sufficiently far from the sun get more methane incorporated into the core. And methane is one of our greenhouse gases. And so it actually acts as a blanket around the core, holding in some of its heat. So this one's a greenhouse effect. I said all 4 of the gas giants would have different stories. With Jupiter, it's leftover heat of formation. Saturn, it's ongoing differentiation in the form of helium rain. Uranus, nothing's going on. Neptune, it's a greenhouse effect caused by methane warming the core. And this drives violent storms. The most famous is called the Great Blue Spot. We saw it when Voyager 2 passed by. We thought it was the analog of the Great Red Spot of Jupiter. But later, Hubble Space Telescope pictures taken in the 90s and 2000s showed that it's gone. They waited, got all sides of the planet, and it disappeared. So it does not appear to have been a permanent storm like on Jupiter. It disappeared. And that could be due to its tilt. And as it moves around the sun, different hemispheres have different seasonal effects that can change the weather. Okay, rings. Plowing through pretty quickly here. Rings, so Uranus has rings. They're thin, piddly little leftover rings. It means there was a great ring system here at one point, but now it's gone. And all that's left is what's held in place by shepherd moons. Same with Neptune. Here Neptune's blocked so you can see the rings more easily, but it also has these thin leftover rings. At some point in the past, there was a great ring system. We've been looking for the shepherd moons, and with the strongest ring going around Uranus, we found them back in '86 with, I think this was Hubble Space Telescope imaging. With the smaller rings, we haven't found the shepherd moons. They're bound to be really, really tiny and hard to see, but they got to be there. So now the moons. I'm just plowing through this here, but certainly we'll get through lesson 8 today, maybe a little bit of lesson 9. Moons of Uranus, we have 5 medium-sized moons and no large moons. Let's start building up a table here. So for the moons, we have Jupiter, Saturn, Uranus, and Neptune. Large, medium. So Jupiter has 4 large, no medium. Saturn 1 large and 6 medium. Uranus has no large and 5 medium. So we see a trend where we're going from large to medium and then also to fewer moons as we get into these smaller planets. So 5 medium-sized moons named after Shakespearean characters. That's the naming convention there. And I'll just briefly mention Miranda, the smallest one here, because it ties into our story of collisions. This moon, if you look at it, it has 2 completely different geologies on this side versus this side. It looks like completely different worlds, and that's what we think happened. We think there was a collision, a gentle collision. Two objects probably moving in the same direction just kind of merged gravitationally. If it was a big, powerful collision, it would have melted the surface and it would have all mixed together. So this would have been a soft landing, gravitationally pulled together, not melting either of their surfaces, just merging. So again, more evidence of collisions even out in the outer solar system. Also, the tilt of Uranus and Neptune is evidence of collision. Then finally, we have the moons of Neptune. We have two medium-sized moons, but one large moon. So Proteus and Nereid are the two medium-sized moons, but then that one large moon, that's bucking the trend. Smaller worlds farther away from the sun, we'd run out of large moons, but yet here we have one. However, it has its own origin story. Oh, here it is with the other 7. It's the smallest of the 7. Triton, it's called Triton. If you're in the lab course, you probably took a picture of it. Triton's orbiting backwards, which means it did not form there. Everything that formed in the solar system was going around in the same counterclockwise direction. It must have been captured. Also, you have Proteus here and Nereid. They're both going the right way, but if you look at Nereid's orbit, I'm going to zoom out now, it's super eccentric, which means it might have been captured as well. Just like the tiny moons going around Jupiter, they're very eccentric. This is, I think, the most eccentric in the entire solar system of all the moons. So it's probably captured, though it may have formed there and its orbit may have gotten disrupted when Triton came in. So it's not guaranteed. Triton is guaranteed. This is the second most likely, and that ties directly into one of the homework questions, which if you didn't hear this and you read that question, you're like, what the hell? How can I answer that? But now it should be pretty easy. So where are these moons coming from? They're coming from the Kuiper belt. Just like Jupiter was getting moons from the asteroid belt nearby, Neptune is picking up these moons from the Kuiper belt, also nearby. Here's Triton compared to Pluto. It shows you that it is actually worth spending at least a few minutes on each of these moons. If Pluto is an important object to you, and it is to many people, Triton and these large moons of the solar system are comparable in size, and sometimes, well, Triton's larger, and Triton's the smallest of the large moons. So the large moons of the solar system are all bigger than Pluto. And we'll talk a little bit more about Pluto in lesson 9 when we get out into the Kuiper belt. Now, it means they should be similar, but their surfaces actually differ. And if you think about it, it makes sense. If Triton was, this is a picture of Triton taken by Voyager 2. If Triton was captured, that would have been a very challenging process. As it came in, I said, like with the capture theory with Earth's moon, it's hard to capture a large world. And this probably wasn't coming in with exactly the right direction and momentum and energy. To capture it probably involved a third moon that ended up with that energy and momentum and was ejected so Triton could take its place. But throughout this process, there would have been tremendous tidal stresses and tidal heating, melting the whole moon. Then it would have re-solidified. And that seems to be the case. The surface has hardly any craters, which suggests that it was reformed, remade recently. It did have a few surprises. We have nitrogen geysers. Nitrogen gas at this cold temperature is black, and it piles up under the surface ice, and depending upon solar illumination, it can poke through. So that was a surprise. We have nitrogen geysers. This pink area is methane ice. Here's one of the few impact craters that we can find on the surface. There aren't many of them, so it's a relatively new surface. This capture happened somewhat recently, and that could be 1 billion years ago, but not near the beginning of the solar system. And this will help. I know I'm at the end here, but I think it's almost my last slide. This will help with your last homework question. Triton is moving towards Neptune, and it makes sense. So here's Earth and our moon and the tidal bulge. Remember back to lesson 6. The moon makes a tidal bulge, but Earth's spinning faster, so it pulls it forward. So this bulge is always in front of the moon, egging it on, pulling it gravitationally, boosting its orbit. So our moon is moving away about 1 centimeter per year. But Triton is orbiting backwards. So there's going to be, Triton will make a bulge in Neptune, but it's not being boosted. It's trying to run away from the bulge. So the bulge is stealing its energy. That means Triton is not moving outwards, but inwards. Our best guesses, and it really is just a guess, is whatever I put in the homework. I think it's 8 centimeters per year. So in that question you're asked, given where Triton is now, and given where the Roche limit is, 2.4 times the radius, and given that speed, how long until Triton hits the Roche limit? When it does, it will be torn apart, and we'll have a ring system more glorious than Saturn's. Saturn's rings, that's produced by a medium-sized moon. This is one of the 7 large moons of the solar system and a smaller planet in the middle of it. So it's going to be a tremendous ring system when it happens. When that will be, you'll calculate in the homework. But it's going to be a long time from now. Don't hold your breath. And by the time it does happen, Saturn's ring system will have fallen apart and look like what Neptune's ring system looks like now, just whatever happens to be held together by shepherd moons. So at different moments in time, you'll have different rings, different sets of glorious rings in the solar system. And sometimes all of them will just be the shepherd moon systems. Okay, that gets us to the end of lesson 8. I did not get into lesson 9, so I'll see what I can do next time. Whatever I can't do, I'll assign by video over the weekend. Okay, thanks a lot.
Professor, I have one more question.
Yeah, go ahead.
Can you
Thank
go
you.
on one more time, like what causes like the ring system to disappear over time?
Yeah, so, they're orbiting around the planet, but they keep interacting with each other, either bumping into each other or tugging on each other gravitationally. And that causes the rings to kind of diffuse and fall apart with time. And the only exception to that is if you're trapped between 2 shepherd moons. Most of the material will eventually work its way down into the planet.
Okay, thank you.
Professor, could you explain Triton and the bulge it makes in Neptune one more time?
Yes, I did that kind of quick. So this is, again, the Earth-Moon system, and it's analogous with one big difference. So you have the moon out here, it creates a bulge in the planet, and since the planet's spinning faster, it carries that bulge forward. And so this bulge is actually a little bit in front of Earth's moon, pulling it forward, boosting its orbit. So very slowly, the moon's orbit's gaining energy and moving farther and farther away. Now with Triton, it's the same deal, except it's going in the opposite direction. It was captured. It's orbiting the wrong way. So instead of the bulge being in front of where it's going, it's behind where it's going. And so the bulge, this offset bulge, is stealing its energy, which causes the orbit to degrade, and Triton will move closer and closer to Neptune with time.
Thank you.
Sure.
Professor,
Could you show the .com, please?
Yes. And I'll make it big.
Thank you.
I had a couple questions about the exam. So how does it compare in terms of like difficulty to the midterms, and what do you think is like the best way to review for it? Like just go over the old tests or look at the homeworks?
Yeah, level of difficulty should be the same as you saw in previous exams, same composition of concept questions versus calculation. There's just gonna be more of them. Again, half of them are exams 1 and 2, so repetition of that material, and the other half will be new stuff from lessons 7, 8, and 9. So to study for the new stuff, you want to look at the homeworks and the warm-up questions. To study the old stuff, you can look at the exams, homeworks, and warm-up questions.
Okay. All right. Thank you.
Can you explain the greenhouse effect on Neptune again?
Yeah, and so we'll learn in lesson 9, when the core of Neptune was made, there was more methane incorporated. You got to be far enough away from the sun and cold enough to hold on to that methane. And so Neptune's core has an overabundance of methane, which is a greenhouse gas. It's, just like on Earth, it's a greenhouse gas. It is out there as well. And it's acted like a blanket around the core, keeping it warmer than it normally would be. And so that extra heat leaks out through the surface. And so that's the source of internal heat for Neptune. It's a greenhouse effect.
Thank you.
Sure.